2 million years is not how long volcanoes typically erupt. It is how long mountain ranges grow, how long entire species exist before disappearing into the fossil record. A single volcanic event of that duration is not a geological incident. It is a geological era. And yet, roughly 252 million years ago, a region of what is now northern Siberia split open and began releasing magma continuously, relentlessly, across a span of time so vast that the entire history of the human lineage would fit inside it dozens of times over. The eruption is called the Siberian Traps. What it did to the planet is called the Great Dying. By the time it was over, 96% of all marine species and 70% of all land vertebrates were gone, not from a single catastrophic moment, but from a sustained cascading assault on every system that kept life possible, an assault the Earth essentially inflicted on itself. The Siberian Traps is classified as a Large Igneous Province, a geological designation for eruptions of such scale and duration that the word volcano no longer quite captures them. Over approximately 2 million years, the traps released an estimated 3 million cubic kilometers of magma, enough to bury a landmass the size of the United States under 2 kilometers of solid basalt. The eruption built, layer by compressed layer, a stack of rock up to 4 kilometers thick across what is now the Siberian Plateau. For paleontologists studying the end Permian extinction, the Siberian Traps presented an immediate conceptual problem. Large igneous provinces are not unusual in Earth's history. Several others are known, and while they disrupted regional environments, none triggered a biospheric collapse remotely comparable to the Great Dying. The Siberian Traps was not obviously exceptional in scale. It was long, immense, and destructive, but so were others. And yet the fossil record at the Permian-Triassic boundary indicates that the extinction unfolded within roughly 60,000 years. 2 million years of volcanism somehow compressed its lethality into a window 60 times shorter. That mismatch is the central problem. Solving it required understanding not just that the traps erupted, but precisely when and precisely where each phase of the eruption occurred. The primary archive for this investigation is a geological quarry in Changsing County, China, known as the Meishan D section. This site serves as the global reference point for the Permian-Triassic boundary. The physical transition between the two eras is visible in a sequence of distinct clay layers. Bed 25, often called the boundary white clay, is an altered volcanic ash containing unweathered high-temperature quartz and clay minerals, including illet and smectite. Above it sits bed 26, a dark carbonaceous mud rock. The transition between these beds coincides with a sharp negative excursion in the isotopic ratio of carbonate-carbon, a geochemical signal indicating a massive, rapid injection of carbon into the global atmosphere. This chemical signature allowed researchers to correlate the marine sediments at Meishan with the terrestrial rock sequences of the Karoo Basin in South Africa, establishing that the marine and terrestrial extinctions happened at the same time. The carbon isotope excursion at Meishan also allowed geologists to correlate the boundary across entirely different rock types and environments. Marine limestone in China and fluvial sediment in South Africa look nothing alike, but the same geochemical shift appears in both. That correlation confirmed one of the essential facts about the Great Dying. The marine and terrestrial collapses were not separate events unfolding on different timescales. They were simultaneous. Whatever hit the oceans hit the land at the same moment. Pinpointing the precise interval within the Siberian Traps responsible for that signal required a different tool entirely. Before the eruption tipped into catastrophe, the late Permian was a fully functioning, biologically elaborate world. Earth's landmasses were fused into the single supercontinent Pangaea, ringed by the global ocean Panthalassa. The southern hemisphere was covered in vast deciduous forests dominated by Glossopteris, towering seed ferns that formed the structural base of complex terrestrial food webs. The fauna that moved through those forests was, by any measure, strange and ecologically impressive. Parasaurs, barrel-bodied herbivores up to 3 meters long and armored in bony scutes, were among the dominant large animals. The ecological pressure they faced came from above the food chain, where the Gorgonopsians hunted. These were lion-sized, saber-toothed predators with elongated canine teeth suited for penetrating the thick hides of their prey. They were the apex carnivores of the Permian terrestrial world, and they had been that for a long time. In the oceans, the seafloors were structured by reef systems built not by modern corals, but by rugose and tabulate corals. Architecturally complex, ecologically rich environments that had persisted through the Paleozoic for hundreds of millions of years. The water column was populated by ammonoids, shelled cephalopods with complex internal chambers, and the seafloors crawled with brachiopods, bryozoans, and trilobites. The trilobites deserve particular attention. They were one of the most successful animal groups in Earth's history, having first appeared during the Cambrian explosion and surviving every major extinction event across more than 300 million years. At the end of the Permian, they were still present, still navigating the ocean floor, apparently no closer to extinction than they had been for hundreds of millions of years. That world did not end because of anything inherent to its biology. It did not end because of an asteroid, or because some internal evolutionary clock ran out. It ended because of what happened underground, in Siberia, at a very specific moment within the long arc of the Traps eruption. The Siberian Traps began as a surface event. For roughly the first 300,000 years, the eruption consisted of massive effusive flood basalts, lava flowing across the landscape in enormous, successive pulses. These surface eruptions were locally catastrophic, destroying vast stretches of terrain and releasing sulfur dioxide and carbon dioxide as the magma degassed. But they did not collapse the global biosphere. The planet's carbon cycle absorbed the output. Life continued. As the eruption progressed, the surface lavas accumulated into a hardened, stacked sequence of basalt up to 4 kilometers thick. This was the accidental architecture of the coming catastrophe. Researchers Seth Burgess and Sam Bowring addressed the timing problem directly through high-precision geochronology. Volcanic eruptions produce ash beds containing microscopic zircon crystals. Zircons are extraordinarily durable silicate minerals that incorporate uranium into their crystalline structure at the moment of formation, while rejecting lead almost entirely. Over millions of years, the radioactive decay of uranium into lead isotopes functions as a precise internal clock. Extracting these crystals from ancient rock requires pulverizing fist-sized samples with jaw crushers, sifting the material through fine sieves, and separating the dense zircons from lighter minerals using electromagnetic sorting and heavy liquid flotation. The recovered crystals are then analyzed by applying a technique called chemical abrasion, which resolves the uranium to lead ratios with enough precision to distinguish dates separated by tens of thousands of years across a quarter-billion-year span. By applying this method to zircons from the ash beds interleaved within the Meishan limestone, Burgess and Bowring dated each stratigraphic layer and correlated those dates directly with the phases of Siberian Traps activity. Their analysis identified the specific sub-interval of the eruption that aligned precisely with the extinction onset. It was not the surface lava phase. Once the surface lava had built a 4-kilometer thick crust of hardened basalt, that crust became an impenetrable structural barrier. Subsequent magma ascending from the mantle could no longer breach the surface. Forced to find another path, it spread laterally through the shallow continental crust as sills, flat, sheet-like intrusions that moved horizontally through existing rock layers rather than erupting upward. The main zircon record, cross-referenced with dating from the Siberian Traps themselves, confirmed that this transition to intrusive sill emplacement coincided precisely with the onset of the mass extinction. Not approximately. Precisely. The critical variable was where the sills intruded. The magma spread directly into the Tunguska Basin, a sedimentary sequence uniquely packed with volatile-rich rock. Vast deposits of organic-rich coal, marine carbonates, and extensive Cambrian evaporite formations, including halite and anhydrite. These were not inert geological layers. They were storing chemical energy, waiting for something hot enough to release it. The magma arrived at temperatures exceeding 1,000 degrees Celsius. What followed was contact metamorphism, the thermal transformation of surrounding rock by direct heat from an igneous intrusion. The baking of coal and terrestrial carbon released methane and carbon dioxide in quantities that dwarfed normal volcanic degassing. Thermal modeling of the Tunguska Basin contact aureoles estimated that the metamorphic reactions generated between 52 and 80 tons of carbon dioxide per square meter, producing 4 to 9.2 times more greenhouse gas than the magma itself would have released through standard degassing. The total volatile output from the sediment baking is estimated at roughly 100,000 gigatons of carbon dioxide. The heating of the evaporite layers, the salt and anhydrite deposits, simultaneously synthesized organohalogens, including methyl chloride and hydrogen chloride, in industrial quantities. The pressurized gases could not remain underground indefinitely. The crust fractured. Explosive pipe structures and phreatomagmatic craters opened across the Siberian landscape, blasting greenhouse gases, halogens, and vaporized heavy metals directly into the stratosphere. The mercury dispersal produced one of the clearest pieces of physical evidence connecting the Tunguska sill phase to the global extinction. As the sills baked coal, they vaporized mercury, which atmospheric circulation carried around the planet. Anomalous mercury spikes appear in boundary sediments on every continent, in the marine strata of China, in the terrestrial rocks of South Africa, in the sediments of Australia. The same chemical fingerprint was deposited simultaneously worldwide. The Tunguska Basin was cooking in northern Siberia, and the exhaust was landing in the southern hemisphere. The 100,000 gigatons of carbon injected into the atmosphere drove global temperatures upward at a speed the biosphere could not absorb. Tropical ocean surface temperatures rose approximately 10 degrees Celsius, pushing them to near-lethal levels around 33 degrees Celsius. That warming set the first of a sequence of lethal thresholds in motion, each one destabilizing conditions for the next. The physiological trap facing marine animals was defined by what researchers call the metabolic index. Cold-blooded marine organisms regulate their oxygen consumption based on water temperature. As temperatures rise, their basal metabolic rate accelerates, increasing their biological demand for dissolved oxygen. Simultaneously, warmer water holds less dissolved oxygen as a physical property. The two constraints converged. Animals needed more oxygen precisely as the ocean's capacity to supply it dropped. Climate models calibrated against paleoceanographic records indicate that the global oceans lost approximately 80% of their total dissolved oxygen content. The geographic pattern of extinction reflects this mechanism directly. Tropical species had some biological margin to migrate poleward. High-latitude organisms adapted to cold, oxygen-rich water had nowhere to go. Their required conditions ceased to exist. The greenhouse warming was not driven by volcanic carbon alone. At the extinction boundary, sedimentary records from South China show a sharp spike in nickel concentrations. Nickel is a trace element delivered to the oceans by magmatic sulfide aerosols settling out of the atmosphere, a direct product of Siberian Traps volcanism. For a methane-producing microorganism called methanosarcina, nickel is a limiting nutrient. Phylogenetic analysis indicates that methanosarcina acquired a highly efficient metabolic pathway. This new capability allowed the organism to consume accumulating organic detritus from dying marine life and convert it into methane. The nickel influx from the traps removed the biological cap on their population. An explosive microbial bloom followed, releasing methane, a greenhouse gas more potent than carbon dioxide, into an atmosphere already saturated with volcanic carbon. The warming accelerated. As surface temperatures climbed, the thermohaline circulation began to fail. This ocean conveyor belt depends on cold, dense, oxygen-rich water at the poles sinking and refreshing the deep ocean. With polar waters warming, that sinking stopped. The deep ocean stagnated, and oxygen in the deep water was consumed without replacement. In those anoxic depths, anaerobic sulfate-reducing bacteria flourished, metabolizing the constant rain of dead organic matter, settling from the surface, and producing hydrogen sulfide gas as a byproduct. These toxic oxygen-depleted zones, a condition geologists call euxinia, expanded upward into the shallow continental shelves where most marine life lived, poisoning organisms that had survived the warming and the oxygen depletion above. Geoscientist Lee Kump proposed that the upwelling of hydrogen sulfide into the zone supported massive blooms of purple sulfur bacteria, in what became known as the Purple Earth hypothesis. Under this model, the oceans discolored visibly, took on a violet hue, and vented rotten egg-scented, lethal gas directly into the lower atmosphere. The hypothesis remains a hypothesis. The evidence supports it, but it is not confirmed, though it illustrates how completely the ocean had reorganized around death rather than life. In the oceans, the convergence of warming, anoxia, acidification, and hydrogen sulfide poisoning eradicated the defining fauna of the Paleozoic era. The trilobites, present in the fossil record for more than 300 million years and survivors of every prior mass extinction, disappeared entirely. The rugose and tabulate corals that had built the reef systems of the Permian seafloor were gone, along with the blastoids, the heavily calcified brachiopods, and most of the crinoids and bryozoans. The structural complexity of the ocean floor collapsed. What remained in the immediate aftermath was largely microbial mats and the scattered debris of a world that no longer functioned. On land, the UVB sterilization and thermal stress killed the Glossopteris forests. Their extinction triggered an ecological cascade with physical consequences recorded directly in the rock. Living forests hold riverbanks together through their root systems. With the trees dead and their roots rotting, the sediment that had built stable meandering rivers began to move freely. In the Karoo Basin of South Africa, the boundary interval is visible as a sudden transition from meandering river deposits to braided stream deposits, chaotic, sediment-choked channels where organized rivers once ran. The landscape itself was unraveling. The surge of dead biomass, billions of trees, continental shelves full of marine organisms, the accumulated organic matter of an entire biosphere dying simultaneously, provided a substrate for decomposers on a scale that had never existed before. Fossilized fungal spores, primarily classified as Reduviasporinites, spike sharply in the boundary rocks, representing an explosive proliferation of decomposers feeding on the planetary die-off. Some researchers have debated whether these spores are fungal or algal in origin, but the proliferation itself is not in question. Something was consuming the dead world at extraordinary scale. The terrestrial food webs collapsed in sequence. The Glossopteris forests vanished, removing the primary productivity base. The parasaurs that depended on that vegetation starved. With the herbivore tier gutted, the Gorgonopsians, the saber-toothed apex predators of the Permian, lost their prey base and followed. The top of the terrestrial food chain was vacated entirely. Crossing the Permian-Triassic boundary did not guarantee survival in any meaningful sense. Paleontologist David Jablonski identified a macroevolutionary pattern he called dead clade walking, lineages that technically persisted past the extinction horizon, but were so genetically bottlenecked, numerically depleted, and ecologically marginal that they never recovered. Certain anomodont therapsids and marine gastropod families, including the Bellerophontidae, survived the boundary event, but lingered for only a few million years before vanishing, unable to establish viable populations in the reorganized early Triassic world. Survival was not a threshold. It was a spectrum, and most of the spectrum ended in extinction anyway. Among those that did establish themselves, the early Triassic fossil record is characterized by what paleontologists call the Lilliput effect, a dramatic, systemic reduction in body size across many surviving lineages. Brachiopods, bivalves, foraminifera, and ostracods all shrank. Smaller bodies required fewer caloric resources, generated less metabolic heat, and offered a higher surface area to volume ratio, making oxygen extraction marginally more efficient in persistently hypoxic waters. The organisms that inherited the post-extinction world were almost universally diminished versions of what had come before. The most famous survivor of the terrestrial collapse is Lystrosaurus, a dog-to-pig-sized dicynodont therapsid. Before the extinction, it was a peripheral, unassuming component of the ecosystem. In the immediate aftermath, it became what ecologists would now call a disaster taxon, a species that hyperproliferates into a vacancy left by mass death. Lystrosaurus fossils constitute the vast majority of early Triassic terrestrial vertebrate material, found across the connected landmass of Pangaea, from South Africa to Antarctica to Asia. Its dominance was not accidental. Lystrosaurus possessed a suite of physiological adaptations precisely suited to the apocalyptic conditions of the early Triassic. Its skeletal anatomy, short, broad hands, and wide knee joints with powerful muscle attachment points, indicates a fossorial lifestyle. It could dig. Burrows provided insulation from temperature extremes, shelter from the elevated UVB radiation at the surface, and protection from what few predators remained. Its skull shows complex maxilloturbinals in the nasal cavity, bony structures that in modern birds and mammals function to conserve heat and moisture by conditioning inhaled air, strongly suggesting Lystrosaurus was at least partially warm-blooded and capable of managing its thermal environment internally. Histological analysis of growth marks in Lystrosaurus tusks from Antarctic fossil sites reveals stress bands consistent with periods of torpor, the physiological slowing of metabolism during extended food scarcity or environmental stress. These stress bands are not uniform across specimens. They vary in frequency and depth, suggesting repeated cycles of dormancy rather than a single prolonged episode. In a world where primary productivity had collapsed, the ability to simply stop needing food for a period was not a marginal advantage. It may have been the deciding one. The predator vacuum left by the Gorgonopsians did not remain empty for long in geological terms, though it took millions of years to fill in ecological terms. The lineage that moved into that space was the Archosauriforms, a group of diapsid reptiles whose early representatives were sprawling, crocodile-like carnivores. Proterosuchus, found in the early Triassic Karoo Basin deposits, was among the first. Its bone histology shows rapid, continuous growth before sexual maturity, a life history strategy that allowed populations to rebuild quickly after environmental setbacks. From Proterosuchid ancestors evolved the Erythrosuchids, including Erythrosuchus, which grew to over 3 meters and developed large hypercarnivorous skulls capable of processing prey at a scale that the Proterosuchids could not manage. Unlike their predecessors, Erythrosuchids had a more upright, less sprawling gait. That biomechanical shift toward a more efficient, energy-conserving posture for active pursuit of predation was not cosmetic. It was the structural foundation from which the dinosaurs would eventually emerge, roughly 50 million years after the Great Dying cleared the ground for them. The full restabilization of complex terrestrial food webs took nearly 10 million years. The Great Dying was not caused by the largest eruption in Earth's history. It was caused by an eruption that happened to intrude into exactly the wrong geology at exactly the right moment. A magmatic event that accidentally sealed itself underground, baked the planet's own stored chemistry into a weapon, and triggered a chain of cascading failures that no single environmental pressure could have produced alone. The lava was almost beside the point. The surface eruptions that built the 4-kilometer basalt cap were a prologue. The story was underground, in a basin full of coal and salt and carbonate, where magma at 1,000 degrees turned the Earth's own crust into the instrument of its near-total biological collapse. What mattered was where the magma went when it had nowhere else to go.